Hi, welcome to part 3 of our series of week 2 brief little mini videos on how to do bits and pieces of coding that you might find helpful in your holiday practice and in working on and thinking about your assignment number 1. Not assignment number 2 yet. Okay, so where were we up to? Last time in part 2, well, let me just click to get back to where we were. Here we are. Okay, we finished looking at function, this sort of stuff here, general stuff about the scope of functions, names of variables and functions, how to call functions, how to use functions, how to declare functions. And now we're going to look at ways of using functions. So not really the syntax of functions, just the use of functions. Okay, let me just go back to our home page. And I started preparing before I started the movie. I started this file. Let's just put in the bits that are missing. So Richard. And the date is the, what is it? It's the 20th March 2008. What's web's file? File used coding. Well, this is Cebra's used. I still sort of haven't said what the file is. It's a simple program to print to manipulate the digits of integers. Alright. Hello world. Right, we're done. We'll leave the includes to io.h because I'm sure we'll end up using that. So suppose well, in fact, let's even start straight away. Number. And the first version of printf, where we just have a format string and no variables to stick into it, and we'll read that number in. So we'll put it count int. Well, what is this number going to be? This is, well, it's just going to be a number. Literally, it's just a program to deal with bits of a number. So I guess number, normally not a very meaningful name because of course integers are number. I guess in this case, let's just start up with that number, and if it starts to look stupid, give it a better name. Scanf, read that number in. Yes, please, we'd like it to be a decimal number, and we call it number, ampersand number. We talked a bit about the ampersand in part 2. Now, if we wanted to get the first digit, say, the last digit of the number, how could we get that? Well, the last digit is what you get if you divide the number by 10 and you look at the remainder. If you think about that, dividing by 10 sort of drops the last digit off and it becomes a remainder. So let's just print it out. Printf %t, the last digit is, and we can just put an expression in here to calculate what the last digit is. Remember, the thing that occurs as the second argument here has to evaluate to be a number, because that will be inserted where the %t is. Let's drop it to the next line. Okay, so we don't want to print the whole number, we just want to print the last digit. %10 means divide by 10 and just show us what the remainder is. Do a whole number division. Oops. Okay, let's build that and see how it goes. Number So suppose we enter the number 1, 2, 3, 4, 5, 6. So 123,456. The last digit is 6. So it's extracted the last digit. What if we want the last two digits? Well, we can just divide it by 100. 1, 2, 3, 4, 5, 6. Last two digits. I have to change the message to the last two digits. 56. Alright, now what if we want the second last digit? Well, that's a problem. We can get the last two digits, but then how do we drop the 6 off? After we've calculated 56, how do we get rid of the 6? Well, that's easy. We divide it by 10. Integer division just throws away the remainder. So it's number percent 100 div, which is a short way of saying integer divide, div 10. The innermost bracket gets evaluated at first, of course, so the rules of maths, I'm sure you remember them from high school, and that gives us the 56, finds the remainder mod 100, and then given that number we strip off the last digit, and that will give us the second last digit. 1, 2, 3, 4, 5, 6. Second last digit is 5. Ta-da! Okay, so you've now seen how to strip out the parts of a number. Suppose we wanted to add up all the digits in a number to get its digit sum. So the number 1, 2, 3, 4, 5, 6, the digit sum would be 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21, something like that. So how could we do that? Well, it's interesting because we don't really know how many digits there are. If we knew it was there were going to be 6 digits, we could just sort of repeat this sort of guff here. Do this to get the second and last digit. We could do something to get the last digit. You've already seen how to do that. And by modding it by 1,000 and divvying it by 100, we get the third last. And we could go on and on and on like that. We could get all the digits. But what if we don't know how long the number is? Ooh, that's tricky. Okay. To show you how to do something like that, we don't need to know any new syntax. We just need to think of a clever way of using functions. This is called recursion. I'm going to show you an example of recursion, not using integer sum, but using on another example that's a bit more interesting perhaps than extracting digits from numbers. And this is a fun sequence that we're going to look at now that I first learned reading the book Gödelescher Bach, a wonderful book that I read when I was a young boy by Douglas Hofstadter. If you can get a copy of that book, it's just absolutely worth having. It's probably one of the best books I've ever read, I have to say. Certainly probably the best in the sense that it's given me the most pleasure. I don't think I could think of a single book that's given me more pleasure than that. It's an excellent book. Now the author, a brilliant guy, Douglas Hofstadter, an American academic, still alive now, though I guess he's getting on a bit, he'd be 60 or so now. Describes this sequence in the book. I have no idea whether he invented the sequence or not. It goes like this. Pick any number you want, say 6. If the number is even, divide it by 2. Well, that's an easy rule to follow, so the 6 would go to 3. And then we repeat on the next number. So we started with 6, that second is to 3, so now we apply the rules to 3. If the number is even, divide it by 2. Well, it's not even, so that doesn't apply. Now we need to know the second rule. If it's odd, multiply it by 3 and add 1. So you can see 3 times 3 is 9, jumping ahead here. 9 plus 1 is 10. So the next sum of the sequence would be 10. And you can see that's even, so we can divide it, and that gives us 5. Multiply it by 3 and add 1, and that gives us 16. And straight away, that's very nice. It goes 16. You can see we'll go to 8 to 4, power of 2, so it's going to all the way down to 1. And interestingly enough, 1 goes to 4, and if you look closely, you'll see we've hit a loop now that'll go on forever. How long did this sequence... As soon as you get to 1, you jump to 4 and you enter a loop. So the interesting question that I'd like to ask today is, given the start number, like a 6, how long will a sequence go until you hit 1 and the sequence begins to loop? As far as I know, certainly at the time you wrote the book, I think it was an open question as to whether all sequences would eventually hit 1. I really should find out about that. Maybe we could set that as that'd be a fun tute exercise, wouldn't it? There's going to be some sort of mathematical proof. I'm going to Google and find out about it, and if there's anything interesting computationally about it, let's set it as a tutor exercise. So we want to write a function to print out this sequence. How are we going to do that? Well, okay. That sounds like a hard problem. Remember, whenever we see a hard problem, instead of freaking out and panicking, we just think, well, I wonder if I could solve this problem by breaking it into some easier problems. Let's think about that. If I'm going to do this in a bottom-up fashion, so let's assemble the components into pieces, and then we'll use those pieces to solve the problem. As I mentioned in lectures, bottom-up is not often a fruitful way of solving a large problem, because you end up with a lot of bits you don't need when you assemble it together. But for a small problem like this, I think bottom-up would be a fine way of solving it. So bottom-up, we think, well, what's the most likely component I'm going to need? And hopefully it's sprung into your mind. Maybe you can't do the whole sequence, but you could certainly write a simple function to do one step. And let's write a function called one step. It's going to take in a number and return the next number in the sequence. So, one step. Yeah, one step's not such a good name. One step's describing what the function does. I really want to know, I'd rather have my function name describe the result of the function, not the action of the function. So perhaps we could call the function next, as in it will give us the next number in the sequence. So it's going to return int next. The name of the function is going to return an int, and it's going to take in what? Int current. So given the current number, that's what the next number will be. Better put a comment here, because it's going to be a bit cryptic with a word like next. Return the next term in the wondrous sequence. Alright, so the next term, well, it's very easy, you remember probably. How do we know if a number's even or not? Well, let's say if is, I'll write a function called is even, but I won't. What about, because it's easier to say, if current %2 is 0, in other words, if the number is even, then what's the output? Well, then the next, I'm going to have to store the answer in something, because I don't want to have a return hiding in the middle here, for reasons that will become apparent later in the course. We're not going to do that. We're going to keep all our returns at the end of our functions, keep our program structured. Let's call it result. Pretty banal name, but it's a clue that it's what the function is going to return. So if the current number is even, then the result is the current number divided by 2. Else the result is the current number times 3 plus 1. And that's just paranoid, even though both stupid left to right precedence and proper arithmetic precedence will make that work. Let's put it in brackets just to be really clear. Okay, so we're really pedantic, but let's do it. It's not going to hurt anyone. Return result. Alright, now, this program obviously is not going to work because it has this sequence drawn in it, but I think that sequence is quite helpful. So let's stick that up at the top. And a program to manipulate the digits of integers, well, it's changed a bit now, hasn't it? So now it's a program to launch out a wondrous, or a wondrous sequence. Okay, enter the start value. Start value. So our program's going to ask, what number do you want to start with? And then it's going to draw the sequence. So if it started with 6, it would print 6, 3, 10, 5, 16, 8, 4, 2, 1. And it'll terminate when it gets to 1. Let's do that. If I start the sequence, read the start value, printf the next number is %d next. The next number after the start. Now, so far we're only printing out one number. I just thought I'd do that to see how it's going, give us a clue. It's not going to like the fact we've defined a function and used a function that hasn't yet been defined when it's in the middle of main, so let's declare it before main. So by the time main sees this line here, it needs to invoke the function next, it will know the function next exists. Let's compile. Syntax error for the semicolon. What have I done? Oh, yeah. Too many parentheses there. Try again. Let's run it. Alright, if I put in 6, we all know the next number should be 3. And if I put in 3, the next number should be 10. That's looking good. Oh, why not be just a bit obsessive and we'll check the whole sequence here, because in a second we're going to rely on this thing terminating. So let's just check for this case, at least it should terminate. 8, 16 goes to 8. Oh, sorry, I missed the 5 to 16 step. Let's check that works. And let's check the 8 to 4. And finally, or second finally, and ultimately, 4 to 2. And 2 to 1. Okay. So, next seems absolutely capable of calculating one. Oh, go away. One term in the sequence. How are we going to find them all? Well, let's write a function now called print wondrous. And it's going to print the wondrous numbers out. When it's finished printing the wondrous numbers out, it's just going to stop printing. So it's never actually going to return a value. It's not going to do anything. So in terms of what we're talking about in week 2, this is a function which has side effects and does nothing else. If it doesn't return anything else, its return type is void. Void print wondrous. And it's going to take in an int, which is the start of the sequence. Int start. Alright, now it's obviously going to use next in some way to print it out. So the start value is going to start, and now we're going to say print sequence. I'm just setting this up now because once I've done all the hard work of writing print wondrous, I'm going to want to click it and run it straight away. I'm not going to want to have to write a whole lot of sort of infrastructure to allow it to run. So why don't I get the infrastructure set up first? And that's just going to make me a bit happier when I get to the end of print wondrous. The sequence starting with is %d is just going to be start and then return that. Was it exit success? Syntax error here. What have I done? Oh, left the parentheses off. I think we can fit all that in one line, right? Okay, it's still visible, so it's fine to put it together like that. Ah, it seems to work. So I'm going to say into the start value, I'm going to enter 5, and it's just going to print out the sequence starting with 5 is soon as it's printed out that is, it returns exit success straight away. So, okay, it's not trying to do anything at all. Let's get it to call print wondrous. Starting with the start value. What's going to happen now when I run it? Think about that. You've probably guessed. Ooh. Implicit declaration of print wondrous was here. Print wondrous. Oh. But interesting. Conflicting types for print wondrous and implicit declaration of print wondrous was here. What's it saying? Well, what the compiler is trying to say with these two seemingly conflicting messages is that the first time the compiler sees print wondrous here, it notices it hasn't been defined, and it's unhappy about that and gives a warning. But it would be prepared to go on oblivious to that, and it will guess a type signature for it. And the type signature it will guess, well, in C, the compiler, if you don't give it a type signature, and never ever don't give it a type signature, but if you don't give it a type signature, it will guess that the function returns an int. So we get a warning that we haven't given a type signature in terms of like a function prototype up the top up here, and then it plows on regardless, thinking, oh, I have seen print wondrous now, and I'm assuming it's returning an int. So it gets down to here and it freaks out, saying, what? You're giving me a definition of print wondrous, but it's not even returning the right type. It's returning a void. It should be returning an int. So both these problems are going to be fixed. Not by me turning that to int, by me getting a function prototype and putting it at the top. So it knows about print wondrous in time. Just has to know about print wondrous before print wondrous is called. And that happens inside the main. Let's compile again. There we go. Yep, terminate whatever we've done. And it's happy. Enter the start value. I'd like to start with, what's our sample? 6, please. The sequence starting with 6 is, and then it does nothing. Well, it doesn't do nothing now. It prints the is, and then it calls print wondrous. And what does print wondrous do? Print wondrous takes in a number and does nothing. Doesn't even return anything, which is fine because it's a void. So print wondrous takes a split second. That's the only effect it has on the program, taking a split second. If at all, it even takes a split second. Clever compiler wouldn't even bother calling it. It'd notice it wasn't used and just sidestep it silently. But let's suppose the compiler did call it. It would take a split second to call and then would return instantly, and then the program's returning. So far, all our infrastructure is set up. We're just not doing any work. Don't freak out about that. That's a nice way of writing programs. If you want to get all the work happening up front, it'll freak you out completely. All the bits will. If something's really complicated and you try and achieve it all, you'll end up with a mess. Much nicer to set your sights lower initially and solve a series of small problems successfully and carefully first, and slowly progress towards the big thing, rather than trying to do the whole thing in one hit. For example, if you were a thesis student, rather than spending 3.5 years just thinking, and whenever anyone says, do you have any deadlines or anything to do, you say, yes, in 3.5 years' time I have to have thought, come up with some solutions, and written a thesis. Probably a better approach would be to set like intermediate deadlines along the way, saying, by this point I have to have done this, and by this point I have to have written a paper, and by this point I have to have written half my thesis. And if you set yourself small, achievable goals that don't freak you out, you're more likely to attempt them and try them and be successful in them and move inexorably towards final success. Whereas if you just have a big, vague, dim, dark, distant goal, like, gee, I want to write a function to print all these bits out, that's almost too daunting to even really start and get a good hack at it. In this case, it's not too daunting. Any sort of experienced or even slightly experienced programmer could probably dive in and get it right by fiddling. But, of course, we're just learning these techniques on small programs, so we'll be able to apply them to more interesting, larger programs next. So, anyway, enough of my yakking. Let's get on writing print wondrous. Okay, well, I'm going to apply this thing of trying to break it into parts. So we've got the start value. What are the two sort of obvious... I'm waving my hands in the air while I'm talking, you can't see, but imagine me standing in front of you waving my hands in a sort of airy-fairy way. What are the two sort of general categories of start values we could get? Well, you're probably thinking, gee, well, start values are more or less the same. I guess we could get odd ones and even ones, and that's true, yes, but I'm not even interested in that level of detail yet. I'm really just interested in the overall structure of the program. So what I'm really after is, for one value, the value 1, the program will stop. for all other values, the program's going to keep doing stuff. So let's ask straight away if it's 1 or not, because if it's 1, we can just stop. If start equals 1, we'll print print 1, full stop, backslash n. And that's how the thing's going to finish. I'd like the output to look like this. 6 to 3 to 10 to 1, and I'd like it to stop there with a full stop. Oh, in fact, let's not stop with a full stop. Let's start with a dot, dot, dot. Yeah, that's heaps better. Okay. Okay. So when it gets to this point, it's going to return printing that and do a new line. In all other cases, when it prints out some value, it'll print out a value, it'll print out the arrow after the value. Notice every one of these is a pair, number, arrow after, number, arrow after. So we'll do each of these together. Number, arrow after. And the final one is a bit special, number, arrow after, dot, dot, dot. Okay, so we've done this case, and this is the only one that ends with a new line, all the rest will run on one line. If it's not, then else, what are we going to print? We're going to print, oh yeah, print out. First of all, we're going to print the number, %d, space, arrow, space, so there's spaces between numbers, start from here. So we're saying if we were at the end, print the terminal case and stop. If we're somewhere else, say hypothetically we're at the beginning, print the first two, and then what am I going to want to do next? Well, I'm going to want to print the rest. I want to print this. What's that? Well, that's the wondrous sequence starting with 3. If only I could print the wondrous sequence starting with 3. That's a really hard problem. Or is it? Hang on, I've already got a function to print wondrous. Print wondrous. And it's going to go, not print wondrous start, because I've already printed the start one. It's after I've printed that, I need to print wondrous of the next. The print wondrous of the sequence starting with the next value. So maybe I'll say something like int next. Oh, what did I call that function? Did I call it next? Int next start. What about, yeah, next start. Int next start equals next start. Print wondrous the next start. Whoa, that looks a bit weird, doesn't it? Now I've defined this in the middle, and probably to be nice I should have done it at the top. Well, I only need it inside the else, but anyway, follow the style guide. Start. Oh, here we go. We'll only compiler to optimize out any minor inefficiencies. And we've got next. Check a comment in here. And the start. So that sort of describes what it does. Okay. Oh, and how do I know it belongs to this function? It's sort of the comment setting the void there. I'll sort of change it onto it. Okay, now let's compile it. Compile's fine, and let's run it. And what did we start with? 6. The sequence starting with 6 is 6, 3, 10, 5, 16, 8, 1. Perfect. Did exactly what we wanted. Well, isn't that crazy? If you've never seen this trick before, which is called recursion, you'll be looking at it going, what? What? That tiny little program can't do all that, and it doesn't seem to do anything clever. What's going on? It doesn't seem to do anything complicated. It all looks very simple to look at. How can it do such a sophisticated thing? Let's look at it. It's just like mathematical induction, if you've seen induction before. The idea is, if you want to do a big job, the journey of 1,000 miles starts with a simple step, or single step. Yeah, something like that. I'm sure someone said that. It's exactly the same. We want to do a big complex job, but we notice that the big complex job consists of a whole lot of small, identical jobs. To be precise, the big complex job consists of doing one small step and then solving the original problem with a slightly, but being slightly closer to the solution. So to print, if we're going to print the wondrous sequence starting at 6, it's exactly the same as printing 6 and the wondrous sequence starting with 3. And to print the wondrous sequence starting with 3, well, that's exactly the same as printing the number 3 and then printing the wondrous sequence starting with 10. And that's what we've said down here. If we get to the end, where are we? If we are at the end, stop. You've got to put this in here, just like in induction, you've always got to have a terminal condition. Am I highlighting? My highlight doesn't seem to be working. What's going on here? It's just like in induction, you need the stopping case. So if the start value is 1, we print the terminal condition. If we're not stopping, well then do a little bit of work in the first bit, and then do the rest. Repeat the whole job with a slightly smaller instance. Voila! Recursion. It looks crazy. It takes a while to think this way, so I'd practice recursion myself. Some interesting examples for you, and some of which will appear in the week 3 tube, are write a function to determine n factorial, because of course n factorial is simply n times n minus 1 factorial. The terminal case is 1 factorial is 1. Well, actually the terminal case is 0 factorial is 1, but I don't mind if you stop it. 1 factorial. Or add up the first 6 numbers. Add up the first n numbers, for example. That function is pretty easy because that's the same as taking the first number and adding up the rest, and adding that first number to that smaller sum. So again, recursion. Sum of the first 6 equals the first number plus sum of the first 5. The last number plus the sum of the first 5. And sum of the first 5 is the last number plus the sum of the first 4. And so on, so on, so on, so on. And what other recursive examples are there? Oh yeah, the code I was going to write, which I haven't yet written, and maybe I won't, maybe I'll leave it as a tutor example, is write a function to add up the digit sum of a word. So, the digit sum of a number. So for the number 321, the digit sum is 3 plus 2 plus 1, it's 6. How could you write a function to do that? Well, easy. Think recursively. It's the sum of either the first or the last number you choose. Get the first or last digit, strip that from the number, and find the digit sum of the rest. Add those two values together, and voila, that's the digit sum of the whole number. Oh, good grief, we're being strafed by a Messerschmitt. It's coming out of the sun. I just duck. Okay, so that's your programming challenge. Have lots of fun in the wonderful land of recursion. And I should say, just to calm you down, that there's no way that recursion is required for task number 1, but you might want to play around with it. It's fun, but it's not required. So you don't have to master this to be able to do task 1, but you do have to master this at some stage, so start fiddling with it and thinking about it now. Probably the only thing I should say about recursion, you could stop listening now and just turn off this DVD. Well, it's not a DVD, but turn off whatever it is. I'm not sure how we'll deliver this. We'll probably just stream it somehow. Maybe it's on YouTube. But if you don't want to turn it off, hang around for 60 more seconds. You might be having the following puzzle when you look at this, trying to work out what's going on. You're thinking, okay, the function called print wondrous starts. It declares a variable called next start. It evaluates an if, and if it goes to this branch of the if, it calls a function, that's all fine, puts a value in our next start that we've set up, that's all fine, and then it calls print wondrous. And, you know, if you're on the ball, you'll probably be thinking, whoa, hang on, print wondrous is calling print wondrous. How's that going to work? Is it going to get all jumbled up? It'll go into print wondrous, but it's already up to this step, so it'll come in and leave straight away or something, or what's going on? No. Every time the function's called, it starts from the beginning. and you could have two copies of the function running at the same time, and they're each at different locations. So print wondrous here is running. The function print wondrous, it's set aside some memory called next start. Gets down as far as here and it calls print wondrous. This function freezes, and a new print wondrous starts with a new next start. And that print wondrous sets up a new next start, which has the same name as your original function has, but of course remember we learned that when a function's running, only that function can see that name, and if that name is reused somewhere else, that's completely fine. It's not the same thing. So next start in this new function would be one smaller, or in this case the next number in the sequence, and we'll toddle along, and then we'll call print wondrous again. So our second instance of print wondrous will freeze, and the third instance will start, and that will go, and then the next one will freeze, and so on and so on. And it could be, if the sequence goes for 100 steps, there's 99 versions of print wondrous, all frozen at this step. And then at some point, the very last one will hit a 1, and it will terminate. And that will let the one, and it will return to the one before it, and that will terminate, and that will return to the one before it, and that will terminate. They'll all terminate because immediately after print wondrous, immediately after you call print wondrous, end of bracket, terminate. So the function terminates after print wondrous. So there'll be 100 of them sitting there waiting, and after the final one's run and printed the one arrow ... they'll all one by one terminate in reverse order, in the opposite order to which they started. And that's one reason why sometimes recursion isn't so popular. It does leave lots of frozen functions floating around, and they all take up a little or possibly a lot of memory depending on how you've written the function. And if they take up a lot, and there's a lot of them waiting around, that's obviously not good. So that's one of the reasons why programmers sometimes avoid recursion. But a well-crafted recursion is a beautiful thing, and properly constructed, it's not to be avoided at all. A clever compiler, in fact, will notice there's 99 of them waiting around, and also will notice that nothing's waiting on those 99. As soon as any of them finish, they're all going to terminate, and no more work has to be done, and it won't bother to keep the frozen copies lying around. It'll just pretend it has, and it won't actually waste any memory. That's called, eliminating tail recursion or something very clever. It notices that everyone will terminate in like a deck of cards at the end when we hit the last one, so it doesn't even bother setting up keeping the memory special for them. Each one can reuse the memory of the previous one. That's a compiler optimization. Don't worry if that didn't make any sense at all. And at this point, I don't think it's appropriate really for us to be thinking about efficiency or saving memory or speed, because any decisions we make now won't be very informed, and we may well make our code messy and ugly and unclear for some perceived speed or space advantage that actually will never materialise. So at the moment, just concentrating on writing beautiful, clean code, and there's no doubt that recursion is beautiful and clean. Okay, I'll see you in part 3.